friends, myself Anish. Today we are going to discuss a research paper on software hardware co-design. So let's get started. So the topic is decade of hardware software co-design. So decade means from the past early 1990s to present. We are going to see how the research paper had described the evolution of hardware software co-design step by step. This is a research paper presented by Vinay Wolf, and he is from Princeton University. So here are the details of the this author. He has done electrical engineering at Princeton University. So let's get started. So what does the decade of hardware software co-design means? It basically starts from the early phase of 1990s, where the basic chip of IC designs come in place. So within the increase of time, it has moved from an emerging discipline to mainstream technology, which is currently used today. So moving it has started in 1990. It was clear that microprocessor-based system design would become an important design discipline for IC designers as well. Since the technology has been emerging, so there is a need of more complex and more number of bit microprocessors to handle the complexities of the data. So researchers developed some basic approaches to the design of embedded software running on CPUs, and their work formed the roots of hardware software co-design methodology. So here some problems would also be there to handle large pre-designed CPUs. First steps. So as we have started studying the research paper, the author mentioned the step-by-step of the evolution of co-design. So first step states the earliest co-design efforts was the SOS system, means emergency system, from Prakash and Parker. It means it mentions the name of the writer of the research paper or the author of the research paper, and they were from University of Southern California, which could synthesize an arbitrary multiprocessor topology and schedule and allocate process into the multiprocessor. So this is how it started, and it went through all the times and following all the laws together. So moving ahead, after the first steps, about a year later, means like 1991 or the mid 1991, the Codesign workshop in Colorado and the CASE workshop in Austria, these are some of the principles, introduced several pieces of significant research that had involved in parallel. Like the research were also going, and they were also inventing the new technologies for researching hardware software coding. So the impetus for co-design. What is the governing body that allows for the growing and development of co-design? So the board level system had used microprocessors, even complex microprocessors. So for around 1980s, for example, automotive engineers control appeared, microprocessor that used fairly sophisticated algorithms to control emissions and fuel economy. Since sustainable development was also an important criteria, so they were considering the emissions and fuel economy too. The main rationale for putting microprocessor into IC is that it made the design of complex digital systems predictable, so that it will come to know that how much resources a particular system is consuming. So here is the diagram in which it has clearly mentioned the target architecture that are combined together. So in another significant early paper, there were so many papers of researchers going into this. So actually we have taken only one paper, so we would not be going into the other parts of the paper, as it shows only the evolution of software hardware co-design from 1990s to present. So let's moving ahead. So here is the analysis of hardware software. What are the consequences or what are the parameters that we need to consider for hardware and software? So designers of both systems had to analyze performance along 3 dimensions. There were 3 dimensions for considering. So dimensions were hardware, software and system. So system is basically the combination of hardware and software. Of these, hardware performance analysis has the most available infrastructure. So this is an obvious thing, because hardware, the natural resources are already available so much. So was the easiest. The goal was to determine the hardware unit's maximum clock frequency. Maximum clock frequency, it means to increase the speed of the quick, so that the designer could evaluate many designs during synthesis. The solution was to use high-level synthesis technique to estimate the longest path through the logic. So as the things are not going so easy, so there were some complexities too involved in these things. So as one of the complexity involved is CPU ASIC system, means American standard. This thing is both a multi-programming and multi-processing system. It can include multiple processors that the designer can interleave on the CPU. It has also include multiple processing elements, so that multiple processes can run simultaneously. So parallel processing is also an important thing for consumption of less number of resources and more number of executions to be taking place. So after the early phase, after the 1990s, here comes the maturation phase. Maturation phase describes the hardware software code design rapidly took off after Codesign and cache workshop, which I mentioned in the previous slide. In the next few years, researchers tackled several problems, and their work made it possible to apply Codesign in a wider range of systems. So when a research is taking place, it should be applied to a real world problems. So they were applying many physical and practical systems. So earlier work also dealt with co-simulation and soon recognized it as an essential component for co-design methodology. So here comes the word co-simulation. Co-simulation means the execution of the program on a software level, so that we can predict the output or the problems faced in a real-time performance of the system. So with mixed level simulation, designers can trade off simulation performance for accuracy by choosing the detail level to which simulate various system components. So after that, we are going to use a term called Ptolemy. After this, they were introduced in another environment which focuses on the co-simulation, as mentioned previously. So this earlier work in co-simulation simulated later work to understand the relationships among various computational models and their unifying framework. So in the continuation of maturation phase, so as the system matures, there are some complexities and development should be involved with it. So here are some more people who are going to research on that. Then some of them were M. Shioda and colleagues, built on STL model to develop the Codesign finite state machine (CVFSM) model. On the data side, the synchronous SDF model evolved to describe multi-rate data-oriented computations as those in signal processing. So here are some more researchers that they are going to research on the same topic of hardware software co-design. So they need to consider an important factor that is called low power co-synthesis. Since power was in huge demand, so as to economy their system and lessen the price in the market, they need to think about the low power consumption also. Moving into the mainstream. Mainstream means after the maturation phase, hardware software partitioning now in present days is now practical design task and for reconfigurable computing. Means like we can customize a computer and each components of the hardware software coding. So here is an example of the mainstream code design of a system: field programmable gate array. So as we were discussing, moving into the next one. So here is an important factor to be considered while co-simulation. Between this, the software languages like C bias the implementation in favor of software. So the C language, suppose for example C language, it doesn't know much about hardware, or there are no library functions to describe the hardware function. So it basically considers the components that is required for a software to function well. While hardware languages like Verilog Basic bias results towards the hardware, so it doesn't know much about the software. So here is a problem that we faced in present time. So an alternative might be to describe the system in two languages, describe some obvious hardware functions in a hardware description language, and describe the rest of the functions in a software language. Consequently, when operations move across the partition, only a relatively small part of the total specification must be translated. So here is an important factor or parameter to be considered while designing code. So here is one more example for SOC design that has become popular in the past few years. Is a platform design. Platforming is a pre-designed architecture design used to build system for a given range of applications. So like it has been in many ways platform-based design is the antithesis of code design. Since designers use the platform largely as is, however, the platform must at some point be able to accommodate the desired range of applications. So design is an ideal way to explore the design space and to create a suitable platform architecture. So this is an important slide which we are going to study about the open problems presently in the code design. So current code design systems are far more sophisticated than a decade ago, as we have reviewed through our research paper. Many systems such as automotive engine controllers or personal digital assembly system use a large 32-bit CPU. So this is one thing. The second thing, researchers are still working to define and redefine computational models for jointly describing hardware and software systems. System level performance analysis is a complex problem that analysts must study under a variety of operating conditions suitable for various application types. So this is the second problem. So third problem what we face now is increased number of embedded systems connect to the internet, which imposes new workload. Since number of system increase, the number of workload on cloud or the memory get increases, and we need face problems for the deadlines such as hard and software deadlines, which can cause the system not to work properly. Moving to the next, here we are going to conclude the presentation by explanation of the challenges and problems in brief. So here what can the challenges for researchers or the people working on the part of code design to make it better? Researchers are still working to refine computation models for jointly describing hardware and software systems. So this is an important factor in which the research should be going. The design of language like these must consider computation models. Like current languages are not as far as currently, so we need to implement a new or more advanced languages to understand the system better. So here is the timeline which I made to brief the paper. So early 1990s we started, and the naming of code design from the research paper we get from. By 1992, research paper shows that maturation phase is there, and hardware simulator has been initiated, and demonstration of autonomy has increased. So by present, current embedded computing systems are far more sophisticated than a decade ago, but we still require a software that understands the advanced level of hardware software code design. So here is the conclusion which I went through. The hardware software code design is informed by multiple disciplines. Computer architecture tells us about the performance and energy consumption of single CPUs and of multiprocessor. Real-time system theory help us to analyze the deadline-driven performance of embedded system computer aided. So the important factor is the real-time system, and the computer-aided design. This thing. Knowledge about all these disciplines has evolved, transformed hardware, software, code design, and art to a science. So it's still an research topic. I see integrated circuits become more complex. The technical challenges for design will also increase, and we need to handle the increasing technology in such a way that efficiency and economy should also be maintained, making this a vibrant field for a long time to come. So here is the end of our analysis on the research paper. Thank you.